A single photon striking your eye began its journey inside a star before our planet even existed. Light is the universe's oldest storyteller, a cosmic historian encoding the deepest secrets of existence within its very essence. It is our only direct witness to events spanning billions of years, from the fiery birth of the first stars to the mysterious force accelerating cosmic expansion. By the end of this journey, you will understand how to read the night sky not as a static picture, but as a dynamic history book written in the language of photons. How can we see back to the very beginning of time itself? And what does the fading glow of ancient explosions reveal about our ultimate cosmic fate? What does it mean that we are built from starlight that has traveled across the ages to reach us now? This paradox of identity is the very reason light can be our cosmic messenger. It travels as a wave, a rhythmic oscillation of electric and magnetic fields that needs no medium to ripple through the emptiness between galaxies. Yet it arrives as a particle, a tiny, massless packet of pure energy called a photon that can strike a single pixel in a telescope sensor. Its wave nature is what creates the beautiful patterns of diffraction and interference, the same principles that allow our most powerful observatories to focus and analyze starlight with incredible precision. But it is the particle, the photon, that physically delivers the message, a discrete piece of information from a distant world, and that message is written across a much broader canvas than our eyes can see. What we perceive as visible light, the rainbow from red to violet, is just one tiny slice of a vast electromagnetic spectrum. This spectrum stretches from long, gentle radio waves that can pass through clouds of cosmic dust to the incredibly energetic flashes of gamma rays born in the most violent explosions in the universe. Every single one of these, from the longest radio wave to the shortest gamma ray, is fundamentally the same light, just vibrating at different rhythms. This is the foundational magic. Because light does not change as it journeys for eons through the void, the information it carries remains pristine, a faithful letter from the deep past. Deciphering that letter, however, requires us to learn its language, a code written not in words, but in subtle shifts and missing colors. An astronomer gazing at the Andromeda Galaxy is not seeing its present reality, but a portrait from 2.5 million years in the past. That ancient light, now finally arriving at their eye, left its home galaxy long before human civilization ever began. This is the profound magic of look-back time, a fundamental property of our universe made possible by the simple, unchangeable fact that light travels at a finite speed. It is not an instantaneous messenger. This turns every telescope from a simple backyard instrument to the mighty Hubble into a genuine time machine. The physics behind this is beautifully straightforward, resting on a simple relationship we all learn: distance equals speed multiplied by time. In the cosmic context, the speed is the constant speed of light, often called c, and the time is the light's travel time across the vast emptiness. When we observe a galaxy 10 million light-years away, we are seeing it as it was 10 million years ago, because that is precisely how long its light has been journeying to reach us. We are not looking at the universe as it is, but as it was, a living fossil record of cosmic evolution. Through our most powerful telescopes, we can witness quasars, the brilliant cores of young galaxies, shining as they appeared when the universe was barely 1 billion years old. We can detect the flash of a supernova in a distant galaxy, a cataclysm that truly happened when dinosaurs roamed our planet, its story only now being delivered to our eyes. This principle is the very cornerstone of all observational astronomy. It proves a staggering truth: the farther out into space we dare to look, the further back in time we are able to see. We possess a unique and layered historical record, with the recent past written in the light of nearby stars and the deepest past etched into the photons from the most remote galaxies. This unparalleled ability to directly witness the past is what allows us to unravel the grand narrative of cosmic history, chapter by ancient chapter. That brilliant rainbow of starlight, however, held a secret code invisible to the naked eye. When 19th-century optician Joseph von Fraunhofer carefully passed sunlight through a prism, he saw more than just a smooth band of color. He discovered the solar spectrum was scarred by hundreds of fine, dark lines, as if someone had drawn sharp, black rules across the rainbow. These mysterious Fraunhofer lines were the first hints of a deeper truth. Light was not just a simple glow, it was a complex message, and these lines were its individual words. The key to deciphering them lies in the fundamental nature of atoms themselves. Every chemical element possesses a unique identity, a specific set of energy levels its electrons can occupy. When light from a star's intensely hot interior passes through its much cooler outer atmosphere, the atoms there act like tiny, selective filters. They can only absorb photons that carry the exact amount of energy needed to bump their electrons to a higher level. This absorption steals very specific colors from the starlight, leaving behind a series of dark lines. Each pattern of lines is as unique as a human fingerprint. The presence of dark lines in a specific pattern is the undeniable signature of hydrogen, while a different arrangement points conclusively to calcium or iron. This was the revolutionary birth of astrophysical spectroscopy. It transformed astronomy from a science of mapping celestial positions into a profound investigation of cosmic chemistry. Suddenly, a faint point of light in the sky was no longer just a star. It became an open book. By carefully reading its spectral barcode, we could determine its precise chemical composition, measure its scorching temperature, deduce the crushing density of its gases, and even detect the powerful pull of its magnetic fields. For the first time in human history, we could know what a distant sun was made of without ever going there. We had learned to read the universe's ingredient list, written in the very light it gave away. The universe speaks not only in colors but in shifts. Just as the pitch of a siren drops as an ambulance speeds away from you, the light from a moving object undergoes a similar profound change. This is the Doppler effect, and it allows us to hear the motion of the cosmos written directly into its light. When a star or galaxy is hurtling toward us, the light waves it emits are compressed, like the crests of a wave being pushed closer together. This compression shifts the entire spectrum of the object, including all its unique chemical fingerprints, toward the blue end. We call this a blue shift. But when a celestial object is racing away, its light waves are stretched out across the vastness of space. This stretching shifts its spectral lines toward the red end of the spectrum, creating a redshift. This simple, elegant principle became the key to unlocking the universe's greatest secret. In the 1920s, astronomer Edwin Hubble was meticulously measuring the spectra of distant galaxies. He expected to find a random mix of motions, some blue-shifted, some red-shifted, but the cosmos revealed something far more startling. Nearly every single galaxy he observed showed a redshift. And the farther away a galaxy was, the greater its redshift appeared. This could mean only one thing: the entire fabric of the universe is expanding, carrying the galaxies along with it like raisins in a rising loaf of bread. Each galaxy's redshift was a measure of its recessional velocity, its speed in this grand cosmic flight. This discovery transformed our understanding of reality. revealing a universe that is not static, but dynamically evolving from a dense, hot beginning. The Doppler shift does more than just chart the universe's expansion on the grandest scale. It lets us detect the subtle, hidden dances of celestial bodies. By measuring the tiny, rhythmic blue shifts and red shifts of a star, we can detect the gentle tug of an invisible exoplanet orbiting around it. The star wobbles slightly toward us and then away, its light betraying the gravitational influence of a hidden world. We can use the same technique to measure the incredible velocities of stars whipping around the supermassive black hole at the heart of our own Milky Way. What was once a silent, still photograph of the night sky has been transformed into a rich, dynamic motion picture, all by learning to listen to the subtle changes in the universe's oldest language. Hubble's discovery was far more than a simple chart of galactic motion. It pointed to a reality so profound it redefined our place in the cosmos. The relationship he found was stunningly simple, yet its implications were earth-shattering. The velocity of a galaxy's recession is directly proportional to its distance from us. We write this as a simple formula, v equals h0 times d. Here, v is the galaxy's recessional velocity, d is its distance, and h0 is a special number we call the Hubble constant. This number is one of the most sought-after values in all of cosmology, for it tells us the current expansion rate of our universe. But this expansion is not what you might intuitively picture. The galaxies are not simply flying apart from each other through a static, empty space like shrapnel from an explosion. The reality is far stranger. It is the very fabric of space itself that is stretching and growing. Think of the universe as the surface of a balloon being inflated. If you glue several coins onto the balloon's surface, as the balloon expands, every coin moves away from every other coin. No single coin is the center of the expansion. The motion is a property of the entire surface. This is precisely what happens to galaxies in our cosmos. They are fundamentally at rest within their local patch of space, but the space between them is continuously growing. This is the critical distinction that changes everything. The redshift we see from distant galaxies is not purely a Doppler shift from their motion through space. It is a cosmological redshift caused by the stretching of space itself during the light's multimillion or even billion-year journey to us. As a photon travels across the expanding cosmos, the very space it is rippling through stretches, and this stretching pulls the light wave along with it, lengthening its wavelength and shifting it toward the red. This single observation, written in the faded light of ancient galaxies, forced a monumental shift in human thought. If the universe is expanding now, then rewinding the cosmic film means it must have been smaller, denser, and hotter in the past. Extrapolate all the way back, and you are led inexorably to a moment of origin, a hot, dense state from which space and time themselves emerged. The faint redshift of a distant quasar is not just a measurement of its speed. It is a direct echo of the beginning of everything, a whisper from the Big Bang itself. That faint, uniform glow Penzias and Wilson stumbled upon in 1964 was far more than a pesky bit of interference. Their persistent microwave noise, a signal that seemed to emanate from every point in the sky, was the ultimate cold case. It was the cosmic microwave background, the cooled and stretched remnant of the universe's first light. To understand this echo, we must journey back to a time when the cosmos was not dark and spacious, but a searing, opaque fog. For the first 380,000 years of its existence, the universe was so hot and dense that it consisted of a plasma, a roiling soup of particles where protons and electrons were torn apart and could not form atoms. Light was trapped, unable to travel any meaningful distance without immediately colliding with a free electron, bouncing around endlessly in a brilliant, blinding glare. Then, in a pivotal moment, the universe expanded and cooled just enough for a monumental transition. Protons finally captured electrons, forming the first stable hydrogen atoms. In that instant, the cosmic fog lifted, the universe became transparent, and those once trapped photons were suddenly set free, streaming across space in every direction. The light that Penzias and Wilson detected with their Hubble radio telescope was that very same light after an unimaginable journey of over 13 billion years. This is the oldest photograph we will ever have, a baby picture of the cosmos. What is truly astonishing is its uniformity. No matter where you point a radio telescope, this afterglow is there, bathing the entire universe in a microwave whisper that corresponds to a temperature just a few degrees above absolute zero. But perfection would have left us with an empty cosmos. It was the discovery of tiny imperfections in this background, minute temperature variations of just 1 part in 100,000, that solved a profound mystery. These tiny ripples, exquisitely mapped by satellites like COBE, WMAP, and Planck, are the cosmic seeds. They are regions of slightly denser gravity, the blueprints for everything we see today. Every galaxy cluster, every swirling spiral of stars, every planet, and every one of us grew from those faint imprints in the primordial light. This ancient whisper does not just tell us about the beginning, it gives us the most precise measurements of our universe's present reality, its age, its shape, and its ultimate composition. For centuries, we believed the cosmos was built from the same familiar atoms that make up our world. But light, our most trusted messenger, delivered a shocking verdict. The universe we see is only a tiny fraction of what is actually there. The first major clue came not from the depths of space, but from the motion of stars within our own galactic neighborhood. By carefully measuring the Doppler shifts of stars and clouds of gas orbiting within spiral galaxies, astronomers could map out their rotation curves, a graph of how orbital speed changes with distance from the galactic center. According to the laws of gravity, stars far out in the galactic suburbs, where visible matter thins out, should be moving much more slowly than those in the bright, crowded downtown. Yet the data told a completely different story. The outer stars were whipping around at speeds just as high as the inner ones. It was as if the entire galaxy was embedded within a massive, invisible sphere of something, a halo of dark matter whose immense gravitational pull was the only thing preventing these fast-moving stars from flying off into the void. This unseen substance does not emit, absorb, or reflect any light, hence its name, but its gravitational grip on the cosmos is undeniable. Then, just as we were coming to terms with this invisible scaffold, light delivered a second, even more profound shock. In the 1990s, 2 independent teams were studying a special kind of exploding star, a Type 1, a supernova, which acts as a standard candle. By meticulously comparing its true intrinsic brightness, known from its light curve, to its apparent faintness as seen from Earth, astronomers can calculate its distance with remarkable precision. When they combined these distances with redshift measurements of the galaxies hosting these supernovae, they made a discovery that defied all expectations. The most distant explosions, whose light had been traveling for billions of years, were fainter than they should have been if the universe's expansion had been slowing down under gravity's pull. The inescapable conclusion was that the expansion of the universe is not decelerating at all, it is accelerating. Some mysterious repulsive force, now called dark energy, is actively pushing the cosmos apart at an ever-increasing rate. These 2 discoveries, both made by reading the subtle messages in light, completely overturned our understanding of cosmic composition. The ordinary atoms that form stars, planets, and life itself account for less than 5% of the total content of the universe. Roughly 27% is the invisible gravitational glue of dark matter, and a staggering 68% is the enigmatic dark energy driving the acceleration. Light has shown us that the grand cosmic story is not just about what shines in the darkness, but is fundamentally shaped by the profound and pervasive influence of what remains hidden in plain sight. The biography of a star is written in the very colors it emits. A single spectrum can reveal a star's mass, its age, and its ultimate destiny, a complete life story encoded in the precise patterns of its light. This celestial classification is made possible by a powerful tool called the Hertzsprung-Russell diagram. Imagine a graph where a star's true brightness is plotted against its color, which directly corresponds to its surface temperature. This is not a random scatter of points, it reveals a stunningly clear pattern. The vast majority of stars fall along a graceful diagonal band known as the main sequence, where a star spends most of its life steadily fusing hydrogen into helium in its core. Where a star sits on this main sequence tells you everything about its character and lifespan. A brilliant, hot, blue-white O-type star, positioned at the top left of the sequence, is a cosmic titan. It possesses immense mass, burning its hydrogen fuel with such ferocious intensity that it may live for only a few million years. Its life will be spectacularly short and violent, almost certainly culminating in a cataclysmic supernova explosion. In stark contrast, a faint, cool, red M-dwarf sitting at the lower right is a cosmic miser. It has very little mass and sips its hydrogen fuel so slowly that it can shine steadily for trillions of years, far longer than the current age of the universe. But a star's spectrum does more than just place it on this grand map. It reveals the specific chapter it is currently living through. The detection of the element lithium in a star's light is a telltale sign of extreme youth, as this fragile element is quickly destroyed in a star's core once fusion begins. Later in life, when a star like our Sun exhausts the hydrogen in its core, it swells into a red giant. The spectrum of such a star begins to show the unmistakable signatures of helium fusion, and even the presence of carbon and other heavy elements created in its hot, dense interior. These are the S-process elements, built up slowly over time, a direct signal that the star has become a cosmic alchemist, forging the building blocks of planets and life. The final acts of a star are also written in light for anyone who knows how to read them. The beautiful, glowing shells of a planetary nebula are not the signature of planet formation, but the final, gentle death sigh of a sun-like star, its outer layers illuminated by the hot, exposed core left behind. The brilliant flash of a supernova, however, tells a far more dramatic story. The shape of its light curve and the specific elements visible in its spectrum reveal the violent collapse of a massive star's core and the frantic nuclear reactions that seed the cosmos with the heaviest elements, from the gold in a wedding ring to the uranium deep within the Earth. By learning to decode this language of light, we can gaze at a faint point in the night sky and know not only what it is, but everything it was and everything it will ever be. For most of human history, our solar system was the only example of planets we knew to exist. That profound isolation ended when we learned to measure the faintest whispers in a star's light. The two most powerful techniques for this cosmic hunt rely on detecting incredibly subtle changes, a tiny periodic dimming or a rhythmic, back and forth wobble in the star's motion. The first method, the transit, is like watching for a microscopic moth to pass in front of a distant searchlight. When an exoplanet's orbit is aligned just right from our vantage point, it crosses the face of its star, blocking a minuscule fraction of the light. This dip in brightness is astonishingly small, often less than 1%, but it is perfectly regular, Each repeating dip confirms an orbit, and the depth of that dimming tells us the planet's size relative to its sun. A deep dip suggests a giant, Jupiter-sized world, while a shallower one points to a smaller, rocky planet like our own. The second technique, radial velocity, listens to the star's song for a telltale shudder. A planet does not simply orbit a stationary star, they both orbit a common center of mass, causing the star to wobble in a tiny circle. As the star wobbles toward us, its light is compressed into a slight blue shift, and as it wobbles away, the light stretches into a redshift. By tracking this rhythmic shifting of the star's spectral lines over time, we can detect the gravitational tug of an unseen world. The amplitude of this stellar dance reveals the planet's mass, a crucial piece of the puzzle. Missions like Kepler have stared at vast fields of stars, discovering thousands of worlds through these fleeting shadows, while ground-based instruments like the HARP spectrograph meticulously measure the wobbles of nearby stars, revealing the hidden giants and Earth like neighbors tugging at them. But the true magic of the transit goes beyond mere discovery. During the few hours a planet is silhouetted against its star, a tiny fraction of the star's light filters through the planet's atmosphere if it has one. By comparing the star's spectrum just before the transit to its spectrum during the transit, we can isolate the specific colors of light that were absorbed by the atmospheric gases. This transmitted light carries the chemical fingerprints of the alien air. We can search for the signature of water vapor, the potential hint of methane, or even the tantalizing, though yet to be found, markers of biological activity. The search for other worlds is a story of engineering and patience, of building instruments sensitive enough to detect a star's breath being taken away by a passing world, and clever enough to read the secrets written in that single, filtered breath. Einstein's revolutionary insight was that matter tells spacetime how to curve, and spacetime tells light how to move. This means that light, our cosmic messenger, does not always travel in a straight line. When starlight passes near a massive object like a galaxy cluster, its path is bent by the object's gravitational field, as if passing through a vast cosmic lens. This phenomenon, gravitational lensing, transforms the most massive structures in the universe into natural telescopes, far more powerful than anything we could ever build. The most dramatic form of this is strong gravitational lensing. Here, the alignment is so perfect that a foreground galaxy cluster can warp the light from a single, extremely distant background galaxy into multiple smeared and magnified images. We see these as brilliant arcs and rings of light, like cosmic mirages, encircling the cluster. Sometimes, a single distant quasar appears as 4 distinct points of light around a central galaxy, its image fractured and replicated by the gravitational well. This cosmic magnifying glass allows us to peer deeper into the universe than ever before. Galaxies so far away their light has been traveling for over 13 billion years. Galaxies that would otherwise be invisible to our telescopes are suddenly brought into view, their features stretched and amplified by this natural lens. But not all lensing is so spectacular. Weak gravitational lensing creates a far more subtle effect. The combined gravity of all the matter in a foreground cluster, including its immense halo of dark matter, imposes a tiny, coherent distortion on the shapes of millions of background galaxies. No single galaxy appears dramatically bent, but by measuring the slight, statistical alignment of thousands of them, how their shapes appear slightly stretched in a common direction, astronomers can create a map. This map does not show stars or gas. It reveals the distribution of the cluster's total mass, the vast, invisible scaffolding of dark matter that holds the entire cosmic structure together. Then there is microlensing, a fleeting and intimate event within our own galaxy. When a compact, dark object like a solitary planet, a neutron star, or a black hole drifts in front of a more distant star, its gravity acts as a tiny lens. For a few days or weeks, it focuses the background star's light, causing a temporary, characteristic brightening before fading back to normal. This technique has revealed a hidden population of rogue planets, worlds untethered to any star, drifting alone through the interstellar dark. Gravitational lensing is the ultimate proof that our universe is not a flat stage, but a dynamic, warped landscape. By carefully observing how light bends on its journey to us, we are not only seeing distant objects, we are literally weighing the unseen and mapping the invisible architecture of the cosmos. These points of light masquerading as stars held a secret that would redefine the word power. In the 1960s, astronomers pinpointed objects with star-like profiles, but with spectra showing such enormous redshifts that they had to be billions of light-years away. For something so distant to appear so bright in our telescopes, it had to be emitting almost unimaginable energy. These quasi-stellar objects, or quasars, became an instant cosmic mystery. Their true nature is even more incredible than their discovery. A quasar is the blazing heart of a distant galaxy, where a supermassive black hole containing the mass of millions or even billions of suns is actively feeding. Imagine a whirlpool of gas and dust on a cosmic scale, a vast accretion disk spiraling inward at nearly the speed of light. The friction within this disk heats the material to millions of degrees, causing it to glow with a ferocious intensity that can outshine every single star in its host galaxy combined. This single, brilliant beacon can be seen clear across the observable universe, a lighthouse shining from an era when the cosmos was young and turbulent. Often, the system's immense magnetic fields channel some of the infalling material and blast it back out into space in the form of colossal jets, stretching for hundreds of thousands of light years and pumping energy into the intergalactic void. But the true gift of a quasar is not just its own raw brilliance, it is how it uses that light. The beam from a distant quasar passes through countless clouds of intergalactic gas on its multi-billion-year journey to Earth. Each cloud, depending on its composition and distance, imprints its own unique set of dark absorption lines onto the quasar's spectrum. It is like a barcode of cosmic history. By carefully reading these stacked lines, astronomers can map the vast, invisible cosmic web of matter that stretches between galaxies, tracing the distribution of hydrogen and helium across billions of years. The quasar's incredible light acts as a backlight, illuminating the faint, wispy structures of the universe itself. So when we observe a single quasar, we are not just studying one monstrous black hole. We are using its radiant beam to conduct a forensic examination of everything that lies between it and us, turning a point of light into a tool for cosmic cartography. A supernova's flash is not merely a brilliant death, it is a violent cosmic birth. For a few glorious weeks, this single stellar detonation can radiate more energy than our sun will over its entire 10 billion-year lifetime. Yet within that overwhelming glare, the light itself tells two very different stories, depending on the nature of the star that created it. The first story is one of gravitational collapse. When a star many times more massive than our sun finally exhausts its nuclear fuel, its own immense weight causes its core to implode in less than a second. The rebounding shockwave blasts the star's outer layers into space at nearly a tenth the speed of light, creating a core collapse supernova. The light from such an event is rich with the signatures of heavy elements forged in the star's final moments. The intense heat and pressure are the only crucible in the universe powerful enough to create atoms like iron, gold, and uranium. Every single piece of iron in your blood, every ounce of gold in a wedding ring, was once forged in the heart of such a cataclysm. then scattered across the galaxy by that explosive light. This is how we are connected to the stars, not just philosophically but physically, built from the ashes of ancient giants. The other story is one of explosive theft. A Type 1, a supernova, begins with a white dwarf, the dense, Earth-sized core of a dead star, locked in a gravitational dance with a companion star. The white dwarf slowly siphons material from its partner until it reaches a critical mass limit, triggering a runaway thermonuclear explosion that utterly consumes it. Because this detonation always happens at the same mass threshold, the resulting flash has a remarkably consistent peak brightness. This makes a Type 1, a supernova, one of the most valuable tools in cosmology, a standard candle. By comparing its known intrinsic brightness to its apparent faintness from Earth, astronomers can calculate its distance with incredible precision across billions of light years. It was precisely this measurement, applied to distant Type 1, a supernova, that revealed they were fainter than expected. Their light told us the universe was not just expanding, but that its expansion was accelerating, propelled by the mysterious force we now call dark energy. So the flash of a dying star serves a dual purpose. It scatters the very elements of life into the cosmos while also acting as a precise ruler, measuring the fate of the universe itself. Even the deepest voids between stars are not truly empty. They are filled with a ghostly sea of gas and dust, a cosmic raw material known as the interstellar medium. This diffuse medium is far from silent, whispering its own story through the language of light. The tiny dust grains, smaller than a particle of smoke, act like a cosmic fog. They do not absorb light evenly, instead scattering blue light more effectively than red. This process, called interstellar reddening, makes distant stars appear redder and dimmer than they truly are, as if viewed through a faint crimson haze. It is the reason the central regions of our Milky Way, hidden behind vast dust clouds, remain shrouded in mystery to optical telescopes. But this dust is more than just an obstacle. It is a cold canvas waiting for a brilliant artist. When a massive hot star is born, its intense ultraviolet radiation floods a nearby cloud of gas, stripping electrons from their atoms in a process called ionization. The resulting plasma, a cloud of free electrons and atomic nuclei, then begins to glow with its own unique light. As electrons are recaptured by atoms, they release energy at specific colors, painting the nebula with ethereal hues. The dominant red glow comes from hydrogen, the universe's primary ingredient, while a rarer, ghostly green often signals the presence of doubly ionized oxygen. These magnificent emission nebulae are cosmic nurseries, their brilliant light announcing the presence of newborn stars and the rich reservoirs of gas that fuel them. Meanwhile, the cold, neutral hydrogen gas that fills the galaxy's dark corners communicates in a much quieter voice. A solitary hydrogen atom consists of a proton and an electron, each with a property called spin. These two spins can be aligned in the same direction or in opposite directions. The opposite alignment holds a minuscule amount of less energy, very rarely, about once every 10 million years for a single atom. The electron will spontaneously flip its spin to this lower energy state. The atom releases that tiny bit of excess energy as a photon with a very specific wavelength, 21 centimeters, which lies in the radio portion of the spectrum. While one atom is virtually silent, the combined voice of countless trillions of them creates a faint but detectable radio whisper that fills the galaxy. This 21-centimeter line is a gift to astronomy, as radio waves pass effortlessly through the obscuring dust that blocks our visible light view. By tuning our radio telescopes to this specific frequency, we can map the distribution and motion of the universe's most fundamental building block, tracing the invisible spiral arms of our own galaxy and measuring the rotation of others. Together, the glowing nebulae and the radio whispers of hydrogen allow us to read the galaxy's ongoing diary. We can trace the cycle of matter from the dispersal of a supernova's remains to its eventual collapse into a new generation of stars, a story of cosmic death and rebirth written in the faint, pervasive light of the spaces in between. Light holds another, more subtle secret in its very direction of vibration. We have focused on its color and its brightness, but the hidden property of polarization adds a crucial new layer to the cosmic story. Imagine a light wave as a rope you are shaking. The rope can move up and down, side to side, or at any angle in between. This direction of vibration is its polarization. In the emptiness of space, this direction is random. But when light interacts with matter, its polarization can become ordered, leaving a distinct signature of that encounter. This is precisely what happens as starlight journeys through the vast clouds of the interstellar medium. Tiny, needle-like dust grains drifting between the stars are not randomly oriented. They are slowly spun into alignment by the gentle, pervasive pull of the Milky Way's own magnetic field. As light from a distant star passes through this forest of aligned dust, the grains preferentially scatter away light vibrating in one particular direction. The starlight that emerges is subtly polarized, its vibrations now predominantly aligned in a specific plane. By meticulously measuring the polarization of starlight from thousands of stars, astronomers can effectively trace the lines of this invisible magnetic scaffold. We can now map the ghostly architecture of our galaxy's magnetic field, a force that guides the flow of gas and influences the very birth of stars. This principle of reading direction from light reaches its ultimate expression in the oldest light we can see, the cosmic microwave background. The subtle temperature variations in this afterglow tell us about the density of the infant universe, but its polarization tells us about its dynamics, its very first motions. When the universe was a searing plasma, photons would constantly scatter off free electrons. The push and pull of gravity in those first instants created tiny, rhythmic compressions and rarefactions in the plasma, like sound waves moving through a fluid. These sonic vibrations, known as scalar modes, left a specific curl-free pattern in the CMB's polarization, a pattern we have already detected. But there is a second, far more elusive signal hidden within that polarized whisper. The theory of cosmic inflation predicts that the violent, exponential expansion of the universe's first fraction of a second should have generated ripples in the fabric of spacetime itself, primordial gravitational waves. These waves would have stretched and squeezed the plasma, creating a distinct, swirling pattern in the polarization, known as B modes. Finding this pattern is one of the most important quests in modern cosmology. It is a direct fingerprint of inflation, a smoking gun from the very moment of creation. Experiments at the South Pole, like the BICEP array, peer through the clearest, driest air on Earth, their instruments chilled to a fraction of a degree above absolute zero, all in an effort to isolate this faint, swirling signature from the polarized glow of our own galaxy's dust. The polarization of light, this simple direction of vibration, thus connects the magnetic fields threading our own galaxy to the most fundamental forces that shaped the entirety of reality, allowing us to listen for the echo of spacetime itself being born. The sheer violence of a gamma-ray burst defies human comprehension. In just a few fleeting seconds, a single GRB can outshine every star in 100 billion galaxies combined, focusing more energy than our Sun will produce across 10 billion years into a searing, focused beam of pure gamma radiation. These cosmic monsters were discovered entirely by accident in the late 1960s, when American Vela satellites, designed to monitor for secret nuclear tests, began picking up intense, unexplained flashes of gamma rays that came from deep space, not from Earth. We now know these flashes are the birth cries of new black holes, erupting from galaxies so distant their light has been traveling to us for billions of years. The story of a gamma-ray burst is told in its duration. Long bursts lasting from 2 seconds to several minutes are the final, desperate screams of the most massive stars in the universe. When such a star, spinning rapidly, exhausts its fuel, its core does not just collapse into a supernova, it implodes directly into a black hole. From the poles of this newborn singularity, ultra-relativistic jets of particles are blasted out at over 99.9% the speed of light. It is these jets drilling through the carcass of the star that we detect as the initial blinding flash of gamma rays. Short bursts lasting less than 2 seconds have an even more spectacular origin. They are the death spirals of the densest objects in existence. When two neutron stars, or a neutron star and a black hole, finally merge after circling each other for eons, their collision creates a new black hole and sprays a maelstrom of material and radiation into space. The initial gamma-ray flash is just the opening act. As the jet slams into the tenuous gas of interstellar space, it creates a shock wave that radiates across the entire electromagnetic spectrum. This is the afterglow, a fading fire that shines in X-rays, visible light, and radio waves for days or even weeks. This lingering glow is a gift to astronomers, as it allows them to swiftly point their telescopes and pinpoint the burst's host galaxy, measuring its staggering distance through redshift. Observing a gamma-ray burst is like receiving a letter from the universe's youth, a direct probe into an era when massive stars were born and died in frantic cycles. But the true revolution came in August of 2017. For the first time, gravitational wave observatories felt the space-time ripples from a pair of merging neutron stars. Just 2 seconds later, telescopes in space saw a short gamma-ray burst from the exact same patch of sky. This single event marked the dawn of multi-messenger astronomy. We were no longer just seeing the cosmos, we were feeling its vibrations. The light told us about the explosion and the elements forged in the merger, like gold and platinum, while the gravitational waves revealed the masses of the objects and the nature of their catastrophic dance. A single, distant flash had become a symphony, telling a complete story of creation and destruction. Even the oldest light in the universe is not immune to the present. The cosmic microwave background, that pristine echo from the dawn of time, serves not only as a baby picture but as an active screen. Its uniform glow subtly altered by everything that lies in its path. One of the most profound of these alterations is called the Sunyaev-Zeldovich Effect. It occurs when this ancient light encounters the modern universe's most massive structures, enormous galaxy clusters. These clusters are not just collections of galaxies, they are filled with a superheated, ionized gas, a plasma so hot it glows in X-rays. As the faint, cold photons of the SIMB travel for billions of years and finally pass through one of these clusters, they run a gauntlet of high-energy electrons. Occasionally, a CMB photon will collide with one of these electrons. In that moment, the photon receives a kick, a tiny boost of energy from the much more energetic electron. This process is known as inverse Compton scattering. The effect on the CMB light is a subtle but measurable distortion. At the long wavelengths where the CMB is brightest, the cluster creates a faint shadow, a tiny dip in the signal. But at shorter wavelengths, the same cluster causes a slight brightening. It is as if you were looking at a vast, uniform canvas, and someone had gently traced the outline of a colossal object by slightly changing the texture of the paint. The true power of this effect lies in its distance independence. For most things in astronomy, the farther away an object is, the fainter it appears. But the strength of the Sunyaev-Zeldovich shadow depends only on the density and temperature of the cluster's hot gas. A massive cluster 10 billion light-years away imprints the same distortion on the CMB as an equally massive cluster only 1 billion light-years away. This makes the SZ effect a perfect tool for finding the most distant, and therefore the earliest, galaxy clusters in the universe, objects that are far too faint to be seen by optical telescopes. By conducting wide-area surveys of the CMB with incredibly sensitive instruments, astronomers are now creating vast, unbiased catalogues of these massive clusters. Counting them across cosmic time is like taking a census of the universe's largest cities. It tells us how cosmic structure has grown from the faint ripples in the early universe into the vast webs of galaxies we see today. And because the rate of this growth is fiercely governed by the tug of dark matter and the push of dark energy, this cluster census provides one of our most stringent tests for these mysterious forces. The CMB is no longer just a relic. It has become an active diagnostic tool, its ancient light continuously revealing the hidden architecture of the cosmos it passes through. Sometimes the universe leaves behind a corpse so bizarre it defies the laws of our familiar world. When a massive star dies in a supernova, the sheer force of its collapse can crush the core into an object of almost unimaginable density, a neutron star. A single teaspoon of its material would weigh billions of tons on Earth, but some of these stellar cinders are born spinning, and they become something even more extraordinary: pulsars. These cosmic dynamos possess intense magnetic fields that channel radiation into narrow beams erupting from their magnetic poles. As the star rotates, these beams sweep through space like the beacon of a cosmic lighthouse. If Earth happens to lie in the path of one of these sweeping beams, we observe a perfectly regular, repeating pulse of light, most often in the pure, clear language of radio waves. The first of these cosmic clocks was discovered entirely by accident in 1967. A graduate student named Jocelyn Bell Burnell was analyzing data from a new radio telescope when she noticed a peculiar, repeating signal, a pulse that arrived with such perfect regularity it defied all known natural explanations. The signal was so precise that the source was half-jokingly labeled LGM-1 for little green men. The idea of an extraterrestrial civilization deliberately signaling us was a serious, if thrilling, possibility. The truth, however, was even more incredible. They had found a pulsar, a rapidly spinning neutron star, its radio beam sweeping past our planet every 1.337 seconds with a clockwork precision that put our best human timepieces to shame. This extreme regularity is what makes pulsars such phenomenal tools for physics. They are nature's most perfect natural clocks scattered across the galaxy. By meticulously tracking the arrival times of their pulses over years and decades, astronomers can conduct experiments on a cosmic scale. We have used them to test Einstein's theory of general relativity with breathtaking accuracy. The most famous example is the Hulse-Taylor binary pulsar, a system where two pulsars orbit each other. By observing how the orbit of this system slowly decays over time, scientists were able to indirectly confirm the existence of gravitational waves, ripples in space-time, decades before they were directly detected. The tiny, cumulative changes in the pulsar's pulse timing provided the first solid evidence that spacetime itself can vibrate. This success has inspired an even more ambitious project now underway, the creation of a pulsar timing array. The goal is to use not one, but a whole network of these millisecond pulsars across the Milky Way as a galaxy-sized gravitational wave detector. By monitoring the incredibly steady ticks from dozens of these pulsars, scientists are listening for a correlated whisper, a faint, low-frequency hum that would stretch and compress the fabric of space between us and them. This hum is predicted to come from the cosmic background of merging supermassive black holes, the titans that lurk at the centers of galaxies. The regular flash from these dead stars, these cosmic cinders, is providing some of the most stringent tests of the fundamental laws that govern our reality, turning the galaxy itself into the most sensitive laboratory we will ever know. The faint, redshifted glow of the universe's first dawn had remained just beyond our sight for decades. While Hubble painted the cosmos in glorious visible light, it was fundamentally blind to this crucial chapter of cosmic history. The James Webb Space Telescope was engineered with one primary mission: to see the light our eyes cannot, opening the infrared window to the universe. This shift in vision is everything, because the universe is continuously expanding. The light from the earliest galaxies has been stretched on its multi-billion-year journey. The ultraviolet and visible light those infant stars originally emitted has been pulled like taffy all the way into the infrared part of the spectrum. To see these first flickers of starlight, we must have eyes that can perceive this long, stretched-out radiation. Furthermore, infrared light acts as a cosmic skeleton key. The dense clouds of gas and dust where new stars and planets are born are opaque to visible light, hiding these nurseries from view. But the longer wavelengths of infrared light can slip between the dust grains, piercing the veil to reveal the fiery birth of stars and the swirling structures of protoplanetary disks. It can even peer through the obscuring dust at the chaotic hearts of galaxies, directly observing the regions around supermassive black holes. To accomplish this, Webb is a masterpiece of cold precision. Its primary mirror is a vast, segmented honeycomb of gold-coated beryllium, spanning 6.5 meters. Gold was chosen for its exceptional ability to reflect infrared light, gathering the faintest whispers from the edge of time. But to sense that delicate heat from the cosmos, the telescope itself must be profoundly cold. Any object warmer than absolute zero emits its own infrared glow, which would easily drown out the faint signals from distant galaxies. This is why Webb carries a tennis court-sized sun shield, a 5-layered technological marvel that maintains the telescope's instruments at a cryogenic -230 degrees Celsius, creating an island of deep freeze in the void. The early results have been nothing short of revolutionary. Webb has captured light from galaxies that existed when the universe was only a few 100 million years old, revealing them to be unexpectedly massive and mature, challenging our models of how cosmic structures first assembled. It has turned its spectroscopic gaze on the atmospheres of distant exoplanets, identifying the chemical fingerprints of water vapor, carbon dioxide, and even potential biosignatures like methane in alien skies. This is more than just a more powerful telescope. It is an instrument perfectly tuned to the specific light that carries the universe's oldest stories, from the ignition of the first stars to the chemistry of worlds that could harbor life. The universe's final chapter is written in the fading light of its most violent explosions and its oldest whisper. Every photon we collect, from the cosmic microwave background to the flash of a distant supernova, adds another piece to a terrifyingly coherent forecast. Cosmologists call this the Lambda CDM model, the standard model of our cosmos, and its prediction is a cold, lonely, and inevitable end. The driving force behind this fate is dark energy, that mysterious repulsive pressure woven into the fabric of space itself. Its influence is not a one-time push, it is a relentless and growing force. As the universe continues to expand, dark energies grip only tightens, causing the expansion to accelerate at an ever-increasing rate. Imagine a vast, dark ocean where every ship is a galaxy. At first, the ships are close enough to see each other's lights, but the ocean itself is stretching, and the farther away a ship is, the faster it appears to recede. One by one, those distant lights will begin to fade. Their light, struggling across the growing void, will be stretched to longer and longer wavelengths, shifting from visible red to invisible infrared, then to feeble radio waves, and finally to wavelengths so long they become undetectable. Each galaxy will cross a cosmological horizon, its final photon delivered, and then it will vanish forever from our view. Our observable universe, the realm we can possibly know, will shrink. The magnificent tapestry of the cosmic web, with its vibrant clusters and filaments, will be torn apart. Galaxy clusters will become isolated islands in an ever-darkening sea, their member galaxies bound together by gravity but utterly alone in the vastness. Within these isolated islands, the raw material for new stars will slowly be exhausted. Existing stars will burn through their fuel, and the diffuse gas floating between them will become too spread out by the expansion to ever collapse into new stellar nurseries. Star formation will cease across the cosmos. The last generation of stars, small, dim red dwarfs that burn for trillions of years, will eventually sputter out. The universe will enter a degenerate era, populated only by the stellar corpses left behind, cold white dwarfs, neutron stars, and black holes, all drifting endlessly apart in expanding, cooling darkness. The temperature will asymptotically approach absolute zero, a state known as the heat death. This profoundly bleak forecast, the story of a cosmos fading into silence, is the ultimate irony. It was deciphered entirely from light, from the brilliant flash of dying stars that revealed the acceleration and the pristine glow of the Big Bang's aftermath that confirmed the initial conditions. The very same light that unveiled the universe's fiery birth now points irrevocably toward its cold and silent end. That same direction of vibration in a light wave can reveal the invisible architecture of force that weaves through the cosmos. Magnetic fields are the universe's great sculptors, yet they are completely undetectable by our eyes. We cannot see the powerful lines of force that stretch from the surface of the sun, guide interstellar clouds, or thread the colossal jets of active galaxies. But when high-energy electrons are caught in these fields, they are forced to spiral along the magnetic lines at nearly the speed of light. This violent, corkscrew motion causes them to emit a very specific kind of light known as synchrotron radiation. The light they produce is strongly polarized, its waves vibrating in a clean, predictable plane. By tuning our radio telescopes to this signal, we can effectively trace the magnetic field lines themselves. The spectacular filamentary wisps of a supernova remnant glowing in radio waves are not just hot gas, they are a direct map of the magnetic turbulence forged in a stellar explosion. The immense jets shooting from quasars, stretching for thousands of light years, are outlined in polarized synchrotron light, revealing the powerful magnetic funnel that confines and directs their incredible energy. A quieter, more pervasive method uses the dust that drifts between the stars. These microscopic grains are not perfect spheres. They are often slightly elongated, like tiny grains of cosmic sand. As they drift through the galaxy, they behave like minuscule compass needles, slowly spinning to align their longest axis perpendicular to the local magnetic field. When starlight passes through this forest of aligned dust, the grains absorb more of the light vibrating along their long axis. The starlight that finally emerges is subtly polarized, and by measuring the direction of that polarization for millions of stars, we can trace the magnetic field that organized the dust. The European Space Agency's Planck satellite did exactly this, creating an all-sky map of this polarized dust emission. The result was a breathtaking portrait of the Milky Way's magnetic skeleton, showing how its lines curve and sweep along the spiral arms, a hidden scaffold for our entire galaxy. These fields are far from decorative. They are a fundamental part of the cosmic machinery. Within a collapsing cloud of gas, magnetic pressure provides crucial support, fighting gravity and regulating the slow, delicate birth of new stars. Across a galactic disk, these fields help confine and accelerate cosmic rays to nearly the speed of light, and their tension influences the stability and the very shape of the galaxy itself. Every time we measure the polarization of a distant source, we are pulling back a curtain on one of the universe's most pervasive and most hidden shaping forces. No single eye, not even one as powerful as Hubble's, could ever capture the full electromagnetic symphony of the cosmos. To truly listen, we had to build an orchestra. NASA's Great Observatories program was that ambitious endeavor, a fleet of 4 pioneering telescopes launched between 1990 and 2003, each a virtuoso trained to hear a specific part of the universe's grand composition. Hubble, the most famous of the quartet, was our master of visible and ultraviolet light. Its crystal-clear vision gave us the iconic, jewel-like portraits of swirling galaxies and glowing nebulae that have defined our modern image of the cosmos. But for the universe's most violent, high-energy screams, we needed the Compton Gamma Ray Observatory. It was tuned to the highest frequency notes, detecting the furious bursts of gamma rays from collapsing stars and merging neutron stars. To observe the searing heat of cosmic violence, the Chandra X-ray Observatory looked at the sky with X-ray vision. It saw the multimillion-degree gas swirling into black holes and the vast, invisible atmospheres of superheated plasma that envelop entire galaxy clusters. And to hear the universe's quiet, warm whispers, there was the Spitzer Space Telescope. Its infrared eyes pierced through the veils of interstellar dust to witness the birth of stars in their hidden nurseries and the faint glow of cool, failed stars like brown dwarfs. The true power of this orchestra was not in any single instrument, but in their combined performance. A visible light image of a grand spiral galaxy from Hubble shows you the elegant dance of its suns. But point Chandra at the same galaxy, and the X-ray data paints brilliant, fiery halos around voracious black holes at its heart. Then turn Spitzer's infrared gaze upon it, and the dark, dusty lanes that appear as empty voids in Hubble's view suddenly blaze with the light of countless newborn stars still wrapped in their dusty cocoons. Each wavelength reveals a different layer of reality, a different chapter in the ongoing story. This multi-wavelength approach is the cornerstone of modern astronomy, proving that to understand any celestial object, we must listen to its entire electromagnetic chorus, from the deepest bass rumble of radio waves to the piercing piccolo shriek of a gamma ray. That faint 380,000-year-old whisper of the cosmic microwave background was not the only message the early universe left for us. The hot, dense plasma of those first moments was a seething, chaotic medium, and within it sound waves traveled. These were not gentle ripples but powerful pressure waves, vast tsunamis of compressed matter and radiation racing outward from every initial density fluctuation. For nearly 400,000 years, these acoustic oscillations rippled through the primordial soup, a cosmic symphony playing out across the entire infant universe. Then, in the pivotal moment of recombination, the music stopped, as the universe cooled and became transparent, releasing the CBM. The pressure that had been driving these waves vanished. The waves froze in place, leaving a permanent, fossilized imprint on the distribution of matter. Each of those original overdensities became surrounded by a single, massive, spherical shell of matter, a ripple in the cosmic pond that had expanded to a staggering size before being instantly preserved. This fossil imprint has a very specific size, a preferred scale known as the Barrian Acoustic Oscillation Peak, which measures about 500 million light-years across. It is a standard ruler etched into the very fabric of the cosmos. Today, we can find this ruler by meticulously mapping the universe on the largest scales imaginable. Projects like the Sloan Digital Sky Survey have used automated telescopes to painstakingly measure the redshifts and positions of millions of galaxies, creating a three-dimensional cartography of the cosmic web. When astronomers analyze this vast map, they do not see a random distribution. They find that galaxies are slightly more likely to be separated by a specific distance, that 500 million light-year scale, than any other. It is as if we were looking at a vast forest and noticing that the trees are consistently spaced, a pattern left over from the forest's earliest beginnings. This pattern is the ghostly echo of those primordial sound waves, the Barrian acoustic oscillations. The true power of this cosmic ruler is that its true size is known from the physics of the early universe. By measuring how large this ruler appears to be at different distances, and therefore at different eras in cosmic history, we can track how the geometry of space has been stretched by expansion. If dark energy were strengthening, pushing galaxies apart more forcefully, the ruler at a great distance would appear more compressed than expected. The measurements show us precisely how the universe's expansion rate has changed over billions of years, providing a powerful and completely independent confirmation of dark energy's influence. We are not just looking at a map of galaxies, we are reading a phonograph record of the Big Bang's first and only notes, using the frozen sound waves of creation to measure the fate of everything they helped create. Our ability to read the universe's history in light hinges on a series of staggering cosmic coincidences. The very laws of physics appear to be fine-tuned in a way that allows atoms to exist, stars to shine, and minds to ponder their glow. This idea is known as the anthropic principle, a philosophical proposition that the universe we observe must be compatible with the conscious life that observes it. Consider the delicate balance written into the fine structure constant. This fundamental number governs the strength of the electromagnetic force, the very glue that holds atoms together and dictates how they interact with light. If this constant were just a few percent larger, atomic nuclei would repel each other so fiercely that stars could never fuse hydrogen, leaving the cosmos dark and lifeless. If it were slightly smaller, nuclear reactions would proceed too quickly, burning through stellar fuel in a cosmic flash, and protons would never bond to form stable atoms. The beautiful, predictable patterns of spectral lines that act as cosmic barcodes would be completely scrambled, rendering the language of light unintelligible. Our entire window into the cosmos relies on this one number being precisely what it is. Furthermore, the universe itself is transparent to the exact wavelengths that carry its most vital information. What if the cosmic microwave background had been stretched into long, useless radio waves by the expansion, or if interstellar dust blocked all infrared light, hiding the birth of stars? Our most powerful telescopes would stare into a silent, featureless void. The fact that we exist in a universe where these specific keys are available, and that we have developed the intelligence to forge them into tools of discovery, forces a humbling reflection. Does the successful use of light as our cosmic probe suggest that the universe's parameters are not random, but are uniquely suited for the emergence of conscious observers who can ultimately comprehend its story? This is not a scientific test in the traditional sense, but a profound recognition that our quest to understand the cosmos through light is deeply intertwined with the mysterious conditions that allowed that quest to begin in the first place. Yet for all its power, light is a messenger with strict limits, bound by the very laws of physics it helped us discover. our cosmic vision is permanently confined by a fundamental horizon. The universe is 13.8 billion years old, and because light travels at a finite speed, we can only see the objects whose light has had enough time to reach us since the beginning. This creates a cosmic sphere of observation, a visible universe with a radius of about 46 billion light-years, a volume that is staggeringly large but ultimately finite. Every galaxy, every quasar, every photon we will ever possibly collect lies within this bubble. What lies beyond this cosmological horizon is forever hidden. There are galaxies whose light has simply not had time to reach us, and because the space between us is expanding faster than light can traverse it, their stories will never arrive. They are permanently over the edge of our knowable reality. A similar, more intimate boundary exists around black holes. The event horizon is not a physical surface, but a point of no return in the fabric of spacetime. Once matter or light crosses this threshold, it is severed from our universe. No signal, no flash, no fragment of information can ever climb back out against the black hole's immense gravity. The singularity at the center, where our understanding of physics breaks down completely, is forever veiled, its secrets locked away behind an absolute curtain of darkness. Even on the smallest scales, light confronts an inherent blurriness. Quantum mechanics tells us that at a fundamental level, the universe is probabilistic. Heisenberg's uncertainty principle dictates that we cannot know both the exact position and the exact momentum of a particle like a photon with perfect precision. The more precisely we pin down where it is, the less we can know about where it is going. This is not a flaw in our instruments, but a basic feature of reality that light itself cannot overcome. And if we try to peer back to the very first instance of the cosmos, we hit another profound wall. Before the universe was even a tiny fraction of a second old, during an era known as the Planck time, the energies were so extreme that our current laws of gravity and quantum mechanics ceased to make sense. Any light or information from that primal epoch, if it could even be said to exist, would be from a realm where space and time as we know them had not yet formed. Its message would be written in a language we do not yet possess the alphabet to read. These are not temporary technological hurdles, but permanent boundaries drawn by nature itself. They teach us a humbling lesson about our place in the cosmos. Light is the most incredible storyteller we will ever have, but it is not an all-knowing one. The universe, in its infinite grandeur, holds deep and profound secrets that may forever remain in the dark, silent, and beyond our grasp. These technological leaps are not distant dreams, but observatories and instruments currently being forged. The extremely large telescope is rising from a mountaintop in Chile. Its 39-meter primary mirror a colossal eye composed of nearly 800 individual segments. This immense light bucket will gather more photons than any ground-based telescope before it, but its true power lies in the combination of that sheer collecting area with extreme adaptive optics. By measuring the distortion of a guide star in real time and flexing its mirror thousands of times per second, it can cancel out the blurring effects of Earth's atmosphere. The result will be images 16 times sharper than those from the Hubble Space Telescope. This is the level of clarity needed to directly image a pale blue dot orbiting a nearby star, separating its faint, reflected light from the overwhelming glare of its sun for the very first time. We will not just infer the presence of an Earth twin. We will see its faint, azure point and analyze its light for the signatures of oceans, continents, and an atmosphere. To peer with even finer detail, we must escape the atmosphere entirely and think in terms of distributed vision. The concept of a space-based interferometer involves flying multiple telescope mirrors in precise formation, thousands of kilometers apart. By combining their light, they create a virtual instrument with a resolution equivalent to a single telescope, as wide as their maximum separation. A fleet of such satellites could achieve a resolution so fine it would allow us to map star spots on the surface of a distant sun, or trace the intricate structure of the accretion disk feeding the supermassive black hole at the center of our own galaxy. It would transform points of light into detailed worlds, revealing the weather on other stars. The photons these giant eyes collect will be analyzed by detectors of almost magical sensitivity. Superconducting nanowire single-photon detectors operate at temperatures just a fraction of a degree above absolute zero. When a single photon strikes the nanowire, it creates a hotspot that breaks superconductivity, producing a measurable electrical pulse before the device resets. This near-perfect efficiency means almost no photon is wasted, allowing us to push observations to the very dimmest limits of the universe. These detectors will be paired with spectrographs of unparalleled stability, instruments so immune to vibration and thermal drift that they can measure a star's rhythmic dance with a precision of a few centimeters per second. That is the speed of a slow walk, the tiny wobble induced by the gentle tug of an Earth-mass exoplanet. This next generation of tools moves us beyond simply gathering more light and into the realm of interpreting its message with a fidelity that borders on reading the cosmic story word for word, photon by exquisite photon. The silent shudder of spacetime itself has given us a new sense. For most of history, our only window on the cosmos was the narrow stream of electromagnetic radiation, from radio whispers to gamma-ray shrieks. Now we have begun to feel the universe's vibrations and detect its ghostly particles, opening the era of multi-messenger astronomy. This is not just an upgrade, it is a fundamental shift from watching a silent film to experiencing a symphony in full surround sound. Each cosmic messenger carries a unique piece of the story, and only by combining them can we hear the complete composition. The landmark event came in August of 2017. Gravitational wave observatories felt the telltale ripple of two neutron stars spiraling together in a distant galaxy. Just 2 seconds later, orbiting telescopes saw a short, brilliant flash of gamma rays from the exact same patch of sky. This single event, a cosmic collision occurring 130 million years ago, was the catalyst. The gravitational waves told us about the dance of the masses themselves, revealing the incredible speed and final moments of these ultra-dense objects as they warped spacetime. The gamma-ray burst, a form of light, revealed the furious jet of energy unleashed by the newborn black hole. But the story did not end there. As astronomers around the world swiveled their telescopes to that point, they witnessed a new kind of celestial firework, a kilonova. This was a faint, rapidly fading glow in visible and infrared light, the signature of a cosmic forge. The violent merger had blasted a cloud of neutron-rich material into space, and in that expanding cloud, atoms captured neutrons in a frantic process that created staggering amounts of heavy elements. The light from that kilonova carried the specific chemical fingerprints of gold, platinum, and other rare elements forged in the cataclysm. In one observation, we learned that the gold in a wedding ring or the platinum in a catalytic converter was likely born in such a spectacular collision. This is the power of multiple messengers. Light gives us the thermal story, the chemistry, and the magnetic fields of an event. Gravitational waves give us the kinematics, the pure dynamics of mass and motion in the fabric of reality. And then there is the most elusive messenger of all, the neutrino. These nearly massless particles interact so weakly with matter that they can fly straight out of the heart of a supernova collapse or a merging neutron star, bringing us a pristine, real-time signal from the very engine of destruction. While we have not yet detected neutrinos from a neutron star merger, They have been captured from a supernova, offering a direct view into the core collapse that light, trapped in the outer layers, cannot provide. By correlating the arrival times and precise directions of these different signals, we can triangulate events with astonishing accuracy and understand the underlying physics in a way no single channel could ever achieve. We are no longer just astronomers, we are cosmic polyglots, learning to speak gravity, light, and particles all at once, finally hearing the universe in its own true voice. Our entire cosmic story is built from these ancient whispers, yet we must confront a profound philosophical truth. Observing the universe is never a passive act. We are not simply receiving a pure, unaltered signal from the heavens. Instead, we are active participants, constructing our reality through the very specific and limited filters we possess. Our eyes, and even our most advanced telescopes, are tuned to a narrow slice of the electromagnetic spectrum. We are deaf to the cosmic symphony's deepest bass notes and its highest piccolo shrieks, hearing only a small part of the grand composition. This means the universe we perceive is not the universe in its totality, but a version rendered for us by the capabilities of our own senses and our technology. We are like listeners at a concert who can only hear the violins, forced to imagine the full orchestra from that one beautiful but incomplete section. The finite speed of light deepens this separation. We never see the cosmos as it is, only as it was. Every observation is a fossilized snapshot, a moment captured in the distant past and delivered to us only now. From this collection of cosmic antiques, from the youthful portrait of a distant quasar to the baby picture of the microwave background, we must assemble a dynamic, evolving model of reality. We are detectives piecing together the story of a living being by examining a series of still photographs taken at different stages of its life. The narrative of the Big Bang, the dark matter scaffold, the accelerating expansion, these are not proven facts we have touched. They are the most powerful and consistent stories we can tell to explain the faint messages, the redshifted light and the temperature variations that the photons bring to us. This act of interpretation even touches upon the quantum world, where the simple act of looking at a particle can influence its behavior. While a distant galaxy is too large for such effects to matter, the principle challenges our deepest assumptions about a detached, objective observer. It reminds us that the act of seeking knowledge can sometimes change the very thing we wish to know. The universe we understand, then, is a magnificent collaborative story written by humanity. It is a narrative pieced together from the fragmented, ancient letters delivered by light. And in this grand, ongoing quest to decipher the cosmos, we are ultimately seeking to understand the nature of the storyteller and our own humble yet extraordinary place within the tale. From the fiery dawn of the first stars to the accelerating expansion driven by dark energy, our journey reveals light as the universe's primary language. It is a continuous narrative written across billions of years, a story we have learned to read. We decode the spectral fingerprints in starlight to know the composition of distant suns. We measure the stretching of its waves to chart the expansion of space itself. We capture the ancient whisper of the cosmic microwave background and receive a baby picture of creation. Every photon that reaches us is a time capsule, carrying a pristine message from a specific moment in the deep past. Every telescope we build is fundamentally a time machine, allowing us to piece together the grand, sweeping epic of cosmic evolution. The deepest mysteries, from the invisible grip of dark matter to the final moments before a black hole's event horizon, are slowly being unraveled by our relentless effort to listen. We now combine the story told by light with the vibrations of gravitational waves and the ghostly passage of neutrinos, hearing the universe's voice in a richer, more complete symphony than ever before. The next time you look up at a dark sky and see those points of light, understand you are not just seeing isolated stars. You are receiving a delayed broadcast from the distant past, reading a history book written across the void. The universe is constantly speaking to us, telling its epic tale in the language of photons. Our greatest task is to remain humble students, to continue listening, and to learn from the grand story we are so privileged to witness.